Well, welcome and good afternoon. Thanks for joining the JASCO Spectroscopy webinar series. Today, I am Sherry Hemmingson, Molecular Spectroscopy Product Specialist for JASCO, and I'm thrilled to be able to convene this session with you today. Let's look at how we'll spend our time together. Start with an introduction to JASCO. Hopefully you're familiar with who we are, but just a brief overview and a review also of fluorescence and excitation emission matrices, just to set the stage for our guest speaker, Dr. Andrew Jock, who is going to speak with us about his novel way of using excitation emission matrices as fluorescence fingerprints of biofilms to assess, remediate, and troubleshoot water quality and biological treatment processes. We'll close with a question and answer session. And please note that you can use the control panel throughout to submit questions as they come to mind, and certainly at the end as well. And we'll look forward to hearing from you then. Well, if you don't know much about JASCO, the Japanese spectroscopy company, it was started back in 1958 by a Nobel laureate infrared spectroscopist, Shinichiro Tominaga, and the R&D and manufacturing facility is located in Hachiochi, Tokyo, Japan. Back in 1972, JASCO incorporated in the US, and we have a demo lab and offices in Easton, Maryland. JASCO offers a full suite of spectroscopy and chromatography products. Many are familiar with the circular dichroism product line and polarimetry, but JASCO also offers HPLC, SFC, SPM, FTIR, Raman, including microscopy and imaging, vibrational circular dichroism, UV visible near IR spectroscopy, and fluorescence, which of course is our focus today. JASCO's been doing this a long time, over 50 years experience in fluorescence, introducing our first system back in 1967. The current product lineup is our FP8000 series, and here you see shown for size 4 of the 5 models, the FP8200, 8300, and 85-8600. Just a quick overview of what they offer. The FP8200, our entry-level model, covers a range of 200 to 900 nanometers and offers routine analysis with exceptional sensitivity and a high scan speed. The 8300 covers the same spectral range, but provides enhanced performance with a typical signal-to-noise in the 8,000 to 1 range with, again, a very high scan speed. The FP8500 is uniquely designed as our high-end materials system to cover bio, nano, and a broad range of photonics applications with highest sensitivity, typical around 8500 to 1, and a very high scan speed, 60,000 nanometers per minute. The FP8600 provides an extended range out to beyond 1,000 nanometers with a slight sacrifice in sensitivity, but more than doubling essentially the scan speed for fast acquisition, especially important with excitation emission matrices. You can see though that the FP8300 really sits in the sweet spot. It offers the best combination of performance and price. It's almost the same sensitivity as the FP8500 and accommodates all accessories. It's probably our most popular system and the one that Andy uses today to share about his excitation emission matrices. JASCO also offers a near IR system, the FP8700, with 2 ranges out to 1400 if you need higher sensitivity, and then out to 1700 if the spectral range is the most important, again with very high scan speed. And much more of this you can find on the website if you're interested. If we're going to talk about fluorescence, I have to show a Jablonski diagram. So just a quick reminder that when we excite a molecule, goes to the singlet excited state, and if it relaxes back down to the first level of this singlet excited state, and then gives off a photon, This is what we call fluorescence, and that's what we'll be focusing on today. Fluorescence is going to have a Stokes shift or a red shift from the excitation wavelengths. So it'll be longer in wavelength. And we can look at this a little more clearly shortly when we look at spectra. What kinds of substances fluoresce? Well, highly conjugated organic systems, many alternating single-double bonds, aromatic molecules, rigid planar molecules, basically all the stuff that Andy is going to talk about today in treated and naturally occurring water, like proteins, dissolved organic carbon, humic and fulvic acids, just to name a few. So Andy will go much more into this. This is wonderful, though, because we have intrinsic fluorescence present to really track and monitor the presence of these species and the profiles of these species in solution. When we look at excitation and emission spectra, I think we're more used to looking at this format where we have intensity plotted versus wavelength, and we see here the excitation spectrum in blue and the emission spectrum in green. It is shifted to longer wavelengths, and this single emission spectrum is the result of exciting likely at the excitation maximum. So if we were to do this on an instrument, we'd fix the excitation monochromator and scan the emission monochromator, resulting in this fluorescence emission spectrum. Okay, so that's pretty common. I think we're used to that. How is it different to collect an excitation emission matrix? Well, one way to do that is, again, set the excitation mono to a single wavelength, scan emission, step the excitation monochromator, scan emission again, and then repeat that over a desired excitation range. What this will result in is a series of fluorescence emission spectra called an excitation emission matrix, or EEM, or EEM for short. So when we step the excitation mono at a defined interval, we get a series of emission spectra, and we can plot it like this, where we look at the intensity of fluorescence versus emission wavelength on this axis and excitation wavelength along this axis. And it's very easy to see the individual spectra. We can see that in this area, at very short excitation wavelengths, around 250 to 275, this band dominates. However, when we get to longer excitation wavelengths, we see that this band here begins to develop more. And so when you have a complex mixture, this really lets you see a true fingerprint. If we zoom in a little bit, we can also see that there are these spikes that are present. That is just where excitation equals emission. And these are the Rayleigh scatter line, essentially, which is also valuable when looking at water systems. More common, though, are visualizations that use 2 and 3D color contour maps. Here we have the 2D map where we have excitation along this axis, emission wavelength along the x-axis, and then for intensity, we use color. So each data point here of color, the little pixels, represent a data point, and blue being 0, red being the maximum intensity. So you can see we have very little fluorescence here, but we have, we can see the one band here, and we can see that we really have the greatest intensity in this area. Users also like to do the 3D color maps, mostly because they're just really cool and you can rotate them around and look at them from different angles, which is useful, but and you can see the intensity of the scatter band here. So there's some nice features to this, but really is most common to use the 2D color map, which, just much like a fingerprint, just like the lines of a fingerprint, you get a detailed spectral fingerprint, which allows you to track how how this fluorescence profile changes as other parameters of interest vary, whether it's, temperature, time, or other species that may be increasing or decreasing. And it's really powerful when used in combination with supplemental data, which is what our guest speaker is going to talk to us about today. Dr. Andrew Jock is the chief scientist and founder of Water Quality Investigations, LLC, known as WQI for short. He received his education BS in civil engineering from the University of Wisconsin-Madison in 1990. He came back in 2005 and completed his PhD at the same institution in 2009 in environmental engineering and a minor in hydrology and secondary emphasis in microbiology. He brings 30 years of experience in the fields of water supply and water treatment, including university teaching, engineering consulting, equipment sales, and public utility service. At WQI, he has pioneered a multidisciplinary analytical approach with specialized methods to provide client-focused scientific investigations to determine the root causes of degraded water quality. He's also developed proprietary water quality tests to help assess the role of naturally occurring biofilm presence in drinking water systems. Specifically, the biofilm indication test, BIT, biofilm activity test, BAT, and the Legionella indication test, LIT. He strives to separate symptoms from problems to minimize inaccurate, often costly solutions that only mask issues, such as unnecessary addition of chemicals or costly construction. So with no further ado, I am really pleased to pass this back to Dr. Andrew Jock. Yes.
So thank you, Sherry, and thank you for giving me the opportunity to discuss our work with this group today. We have much we could cover today, but with limited time, we're obviously only going to scratch the surface of this topic of biofilm. After this talk, I hope everybody will see why we need to consider the role of biofilm in assessing and managing drinking water issues, which is not common practice in our industry. So what I'd like to start off today is really what is the definition of biofilm? And I have a graphic representation here that we will discuss. So biofilm is basically common soil and water bacteria that are buried in a complex matrix of secretions and products. Think of this as their home. Biofilm is often termed EPS, which stands for exopolysaccharides, and it shows in this graphic representation. However, biofilm consists of much more than that, and it consists of many different biological secretions, including proteins and enzymes, microbial byproducts, which are really leftover scraps of their consumption and using nutrients in the water. We often see organic acids, various different forms of organic acids in the water. And then we find these bound corrosion products, which we call substrate leaching in this graphic. And that's all what's really buried in this, what's considered biofilm. It's important to understand that every surface within a water containing system will naturally develop biofilm. We find it everywhere. We even see it in type 1, ultra pure type 1 water systems in labs. And it's a challenge that labs maybe don't realize that they face, but we do see it in that type of system. This graphic representation, even though it is complicated looking, it's an overly simplified depiction of what biofilm is. The picture in the upper right-hand corner is a graphic representation of, it shows what biofilm is in a water main that was shortly after it was removed from an active water system. So this pipe was in service just prior to it being removed. When we analyzed that material, it was very, very much alive, and it had very, very much of all these secretions that we talked about just a little while ago. If food is plentiful in water and environmental stress is low, we typically find bacteria present, and they'll be happy, but they won't be in a biofilm form. So we see that as planktonic growth in this graphic. However, if bacteria become stressed, they will form a biofilm in order to reduce the cause of their stress, and which we'll talk about more in a few minutes. So what this graphic shows is why biofilm can be a problem in drinking water systems. It shows biofilm on the surface of the pipe, corroding the pipe, with the reason for that being that it's looking for nutrients. We see this associated with plumbing corrosion to cause release of lead and copper and zinc, which we call microbial-induced corrosion. We see it in attacking aquifer minerals to cause corrosion, and it's actually unintended corrosion, and that often releases radium and some other metals that the bacteria might need. We also see it with, in attacking pump or treatment equipment to cause corrosion, which then releases iron, manganese, and zinc to the water. What this graphic does not show is that biofilm can also cause issues, many different issues, including plugging of pumping equipment and piping. It can cause taste and odor issues from the well or even at the consumer tap. It often causes discolored water, and we see that momentarily at well pump startup or even at the tap. It can form disinfection byproducts, which is the reaction of biofilm components with chlorine, or volatile organic carbons, which is the reaction of biofilm with just natural components that are in the water. The takeaway message here is that biofilm needs to be part of drinking water testing. This approach is needed to identify the true source of water quality and corrosion issues so that the solution does not make the matter worse. So our talk today will cover these 4 general points, though not particularly in this order. We'll briefly discuss our journey in water quality investigations and biofilm testing. Along the way, we will discuss typical water quality problems we see in drinking water systems, give an overview of our biological or biofilm focused testing approach, and describe how we use this testing approach to solve various water quality and corrosion issues. Our testing discussion, testing discussion will provide insights as to what EAMs tell us and how they fit into our overall testing and analytical approach. So I'd like to start off today with really these 3 basic concepts that we've developed through our approach. The first concept is that most water quality issues start at the source. And what this refers to is the quality of the source water will dictate what happens in the distribution system and downstream, or even what happens in the infrastructure itself. The second point is that most, if not all, water quality issues will have a microbial component to it, or biofilm component to it. This refers to source water that will promote biofilm and biofilm-related water quality and corrosion issues in the system, which then can become amplified with excessive growth in the infrastructure and the system. That system being the big pipes in the road or the small pipes within a residential or a consumer's building. The third concept is that optimized biofilm control will minimize these water quality issues in the distribution system. And this refers to controlling biofilm through various means versus the standard approach of building some infrastructure or throwing chemicals at the issue. And often we're treating the symptom in that case versus the true underlying problem. So let's briefly discuss our investigative approach, how our investigative approach has evolved, so we can see how we came to using EAMs. In talking about this, keep in mind our primary focus is really quick representative tests to determine where we should look and what advanced testing we should perform so that we can cost effectively solve our clients' water quality or corrosion issues. This graphic shows us the tests that we've used or considered, so there's a lot of information on here. But what I want to focus on is these 4 tests that we do perform on a regular basis. We do a little bit of DNA testing and microscopy as warranted, but mainly these are the 4 tests that we use. So ATP stands for adenosine triphosphate. It's the energy molecule that's present in every living cell and can be used to quickly estimate bacterial presence in a sample. We use this to basically replace enumeration by microscopy, which is very, very slow and time consuming. With this method, we quickly find, when we instituted this method, we quickly found that many of our water quality issues were more than just bacterial issues. They were really biofilm issues. The ATP test is great for looking at bacterial presence, but it's not really, and it's on the bulk water, but it's not really helping us on the biofilm side of it. So after adopting the ATP test, we started utilizing and developing biofilm methods into our investigations to handle that side of the bacteria and the biofilm component in the water quality issues that we were seeing. So our EAM testing, our EAM-based testing is based on the work performed by USGS on surface water assessments. That's what introduced us to it, and we've taken it much further now in drinking water. We see it that it's a quick and easy method to provide a good qualitative assessment of whether a sample contains or was in contact with biological matter. And what we're looking at is the secretions. The bacteria and biofilm are putting secretions in the water, and we're looking for that with this EAM. While it's a good method, it does require good control and good process and a good understanding of context, which we'll talk about in a little bit. This method doesn't answer all the questions, but it provides basically needed direction in our investigations and helps us understand what we need to look for in additional testing. The EAMs are the basis of our biofilm indication test, which we term BIT. And a version of this biofilm indication test is the Legionella indication test, which we call LIT. So based on the EAM testing, we developed a method to quantitatively assess the presence of biologically active products secreted by biofilm, which helps us then understand the root cause of biofilm and why biofilm is present and what it's doing to affect water quality. That test is our biofilm activity test, which we term BAT. This is just a quick look at our BIT test. And a version of this would be our LIT test. There is much information on this that we won't go over, but just in a nutshell, the test, these tests really interpret results against patterns we've identified based on analysis and correlation of over 4,000 drinking water samples. We've tested more than that over the last 4 years, but that's the basis of our database and basis of our BIT test for the correlations that we see. We spent thousands of samples just doing research to understand these patterns better with different molecules and how they respond then from a fluorescence perspective. So the test can quickly assess, what we see is that the BIT test can quickly assess the nature of a water quality issue, which we'll show you in some of the examples coming up. This slide shows examples of biofilm with pictures providing examples of biofilm and environments that we've investigated, and the pictures provide a brief description of what you're seeing here. What we generally found is that discolored water obtained from a drinking water system or a well is water that has been impacted by biofilm. The data are very, very clear on this. We found that discolored water will nearly always contain high metals, and those high metals are often attached then to high bacterial counts. So the metals and the bacteria go hand in hand. We often see that discolored water then has changed water quality compared to its source, and it will contain biologically secreted molecules, which create water quality concerns and potential drinking water violations.
Andy, I hate to interrupt. I just, I think we might have a lag because I don't see that slide. There we go. It just came on.
Okay.
So, yeah. Sorry, I just wanted to let you know there might be, maybe there's a lag.
Okay.
Go ahead.
All right. Thank you. When we see discolored water, we need to ask, is this a problem or a symptom of a bigger issue? And not just automatically go down the path of assuming it's uniform corrosion and throw chemicals or an unnecessary treatment process at it. What our work really indicates is that what happened in Flint, Michigan was a massive biofilm sloughing event caused by a rapid and dramatic change in water source. And by this I mean switching from water from Detroit, which is treated like Huron water, to water from Flint, which is treated Flint River water. Flint was, what happened in Flint was not a new problem, rather an old problem that was lurking in the shadows waiting to happen. The problem was caused by our industry's lack of recognition of the impact that biofilms have on water quality. We see it happening in a lot of systems other than Flint. The treated water from the changed source in Flint while meeting all regulations, was vastly different than water from Detroit, which challenged equilibria that was established in that water system over many years and caused a massive biofilm release and the release then of biofilm-bound metals, hence the violation with lead. Picture 6 on this slide is that of the inside of a toilet tank. I put this up there because this is the best location to really assess the quality of water within any building. And I suspect now many of you, when you go home, will probably look in your toilet tank and see really what kind of water quality you have in your building. Hopefully it's not as bad as what this picture shows. So let's cover why biofilms form. Biofilm formation is nothing more than a stress response. I indicated that earlier. The first stress that biofilm will cause biofilm really is this change in temperature, where cold water going to warm, or even warmer surface waters going into cold, which can happen seasonally depending upon your geographic location. It can happen when cold groundwater or surface water gets exposed to warm homes. It can happen as we take our drinking water and put it into hot water plumbing systems. And it can even be further stressed when we take that hot water system and recirculate it and give it high water H. The second stress is disinfection, which causes various secretions in an attempt by the biofilm to protect itself. It basically wants to protect its livelihood. We often find that biofilm is thicker and more corrosive in chlorinated systems, and even thicker in chloraminated systems, which is counterintuitive because these disinfectants are supposed to kill, but yet we see a response in that they want to protect themselves. The third stress is nutrient balance, which refers to the balance of carbon, nitrogen, phosphorus present in the water, the amount of metals, the micro amount of metals that are needed for growth, energy and growth, and then energy and oxygen in the water that are there, that are required to basically build biomass. The bacteria are just nothing more but little biomass factories, and they only want to replicate. Bacteria don't have hands like humans, so when something is missing in their diet, they secrete various products, which we talked about earlier, in an attempt to find or release nutrients from their environment. That's why they secrete the organic acids or the proteins, because they're trying to mobilize and grab a hold of it, and that's their hand. And this nutrient limitation includes categories such as starvation, where one nutrient is completely missing. So let's say ammonia is not there at all, so that causes stress. Or there's a nutrient imbalance where all the nutrients are present, but they're slightly out of balance, meaning that they're trying to manufacture more bodies, but they don't have enough to complete a body. It's like building a car and leaving one wheel off, so they're stressed and they want to build that wheel so they can complete the body. The other one in this category is the presence of complex nutrients, which is complex matter that needs to be degraded in order to be consumed and turned into biomass. And we see that with predation on dead cells, decaying organic matter. It's important to know that biofilms are everywhere in our environment, and they're naturally occurring in drinking water. So every water surface will have biofilms in them, and we really only need to be concerned about them in drinking water when they start to affect water quality. So I don't want people get afraid of biofilms. They're natural. When they got out of hand, that's when we see problems occurring. So here we're going to talk a little bit about EAMs, and Sherry already covered this, so I'm not going to recover all of that. The graphic to the right shows an EAM that we collected on a water sample. All of our EAMs are performed on filtered samples, so we are looking at dissolved components and we're removing interfering agents, and that way it provides us a consistent basis for comparison. All of our EAMs are generated using consistent instrument settings and have been developed to create a smooth appearance based on our excitation-emission pairs and time to take a sample. All cuvettes are subject to rigorous storage, cleaning, and QA/QC protocols. That way we don't interfere or we add a bias into our samples. We want the reading to be the sample itself. The assessment categories on the left show how the data behind an EAM can be analyzed. This is based on the published work from Arayal et al. In the reference work, what we've done is we've removed the reference regions from our approach, but we found that the regions were too rigid and not necessarily all inclusive. The work we referenced was from the USGS. We're looking at drinking water, so there's a difference there. We do classify our EAMs basically as MBP EAM and DP EAM. MBP EAM refers to microbial byproducts EAM, which generally associates with the red region, the red lettering in the reference work, and we're looking at these active biological molecules being present. And the DP EAM refers to the decay products EAM, which generally associates with the blue lettering in the reference work, and we're looking at these decay products or these products that are being secreted because we've got complex stuff in the water. So while this general background, I'd like to transition to these examples, these general examples in the following slides. These examples will give you a general understanding of how EAMs can be used in some of the water quality problems that we see, as well as how do we interpret that data to solve the solutions. So I'd like to start with this example, which is a brief look at a plumbing system that had copper corrosion and water odor issues. There's much data here, so I'm not going to focus on all the individual points. We looked at, the assessment looked at water coming into the house, because that's what we're starting with, and then at key points along the plumbing system determine where the problem starts. What we generally found, excessive biofilm at the influent of the home, which is coming from the water system, that worsened as the water flowed through the plumbing, and we can see that in the EAM patterns as they change from influent, softener, hot water, and the ice maker. And now this home is hooked onto a public water system that has really good water, so this is kind of a shock. Further analysis showed that the home has an oversized water service line. I believe it was a 2-inch line because they have a private fire suppression system in the home. Because of the service line issues, then the biology coming in, the water softener became a breeding ground for bacteria and biofilm and basically made the problem worse. The hot water system then, after the softener, amplified the problem, which is seen in a very large increase in the total products EAM, almost doubling from the influent to the building. We solved this problem in this home by performing increased maintenance, which included flushing of the service line. So they actually flush that service line twice a year to remove the biofilm as before it comes into the house. They do enhanced cleaning of the softener, and then they do air scour cleaning of the plumbing. And with that, they've been able to control the odor and the corrosion issues. Important to note here that what we see could happen in any home, especially a home that has low water usage. That's going to replicate somewhat of a oversized service line where we just have these high stagnant conditions. In this example, we show a commercial building that had corrosion issues. The building experienced pinhole leaks within 1 year of occupancy after brand new construction. The owner of the building complained of a strong sulfur odor to the water, which was not present at occupancy. So the normal process would be, let's treat the water for the sulfur. So what we did, though, is to assess the cause of corrosion and odor. We sampled the nearby city well, which was located 3 blocks away, the service entrance to the building, and a distant location in the building to see, is it coming in? Is it from the city's well? Is it coming into the building, or is it in the system itself? You can see that between the well and the service entrance to the building, again, 3 blocks apart, the total EAM went up by an one order of magnitude, so 10 times larger, and the microbial occurrence went up 2 orders of magnitude, so 100 times larger compared to the city's well, just 3 blocks away. This is clearly a biofilm issue in the service line that is caused basically by the presence of starved bacteria. Here, the service line to this building, this water service coming into this building was oversized. The owner of the building decided to save money, which is a common practice here, and take this fire suppression line for the fire suppression system in the building, an 8-inch line, and tap their domestic service off of it. So this is pretty common out there. And in this location, because of the very low usage, and this 8-inch line, the water barely turns over once per day, it created these stagnant conditions, which then allowed the biofilm to grow excessively. The issue was resolved by putting a flushing port on the service line and flushing the water to waste aggressively twice per year at about 800 gallons per minute. And that solved the odor issues. We did this investigation 2 years ago. I talked to them recently, and it has solved their issue. What we're seeing here is a conflict, basically conflicting codes at play. We have water quality codes versus fire protection. That's a common practice in the industry to do what they're doing, but yet the end result is it winds up with a corrosion problem and a water quality problem in their building. This example is about a community. It's a municipal community that was recently out of compliance with the lead copper rule for lead. We're showing here a profile sampling event that was performed at a residential location. This is used to assess the source of lead in drinking water at a location. The flowing sample was collected, and this here was collected prior to stagnation and represents fresh water from the water distribution system that filled the plumbing system all the way from the distribution system main to the tap. We fill that, we basically flush that system and fill it with fresh water at the start of stagnation, or this 6-hour period, to say, what did we start with? And that's what the flowing sample is. After a 6-hour period then of non-use in the home, we flow and sample in 1 liter increments everything between the tap and the distribution main, and we analyze that. The 9.5 liter sample on here represents the water that had been stagnated or located in the middle of the lead service line and had been sitting there for 6 hours. We call it the 9.5 liter sample because it's between the 9 and the 10 liter sample, and we grabbed our sample in between there. We see here there is an increase in microbial occurrence, which is the ME per milliliter, and an increase in EAM between when we compare the 9.5 liter sample to the flowing sample. And this can only happen if two things, this can only happen if biofilm is present when we have a high disinfection residual. So we had disinfection residual coming into this building. For that change to occur, in the face of disinfection, biofilm has to be present. And the biofilm is showing an increased EAM, and it's also giving off increased microbial occurrence. The material inside the pipe, so the flowing sample, following doing this profile sampling, they actually replaced the lead service line, and a section of it was sent to us for analysis, which is shown in the picture on the lower left. The arrow is pointing to loose material inside of that pipe, which is biofilm, and we scrape that off for analysis. 1 gram of this material was scraped and added to 100 mils of ultra pure type 1 water, which basically has no EAM. When we added that 1 gram of material to the ultra pure water, and then we filtered that sample to remove the particles, we can see that material with all its secretions increased our total EAM to almost 2.4 million fluorescence intensity units. And in that sample then, we tested and we found 35,000 microbes per milliliter, which equates to 3.5 million microbes per gram. If we normalize this, we see that that material basically added 236 million fluorescence intensity units per gram. And that's really the dissolved components. That's not the particulate component. And in that dissolved component, that's mainly dissolved organic content, which we see as an increase in FADOC. So FADOC is really fulvic acid, dissolved organic carbon. It's an estimate of the organic carbon content that's present in the water based on a UV scan. These results represent dissolved biological secretions added to ultra pure water from biofilm, which honestly is happening in every water system. It's just that whether or not it's out of control to cause a problem. The issue here for this system is the excessive presence of biofilm that is basically ignored by drinking water regulations. The lead corrosion problem in this system won't go away until biofilm is managed. Here we have a well assessment. This well is out of compliance with nitrate standard with a highly variable nitrate history. We see high nitrate. When we see high nitrate, it's usually caused by biological conversion of ammonia or proteins to nitrate in the shallow groundwater or soil. Sometimes nitrate is caused by excessive biofilm in the well. Regardless, biology is always involved in the creation of nitrate when we're considering groundwater. We investigated the well to assess whether the issue was in the well borehole or the aquifer, and determine why the nitrate was variable. The EAM shows a borehole sample which was collected shortly after startup. This sample represents water that was sitting in the well just prior to startup pumping. The EAM also shows, there's also an EAM for an aquifer sample, which was collected after about 120 minutes of continuous pumping. This sample represents water that was sitting outside the well in the connected aquifer prior to startup pumping. When we see EAMs, in the EAMs, we see nitrate in water from the aquifer being consumed by excessive biofilm in the well. This is a process called denitrification. The arrow shows the nitrate band present in the EAM from the aquifer at a wavelength of 215 nanometers. We see nitrate peak absorbance, or an absorbance of nitrate there, and that correlates with an area where we don't see any fluorescence on the EAM. That nitrate band is absent in the EAM from the borehole sample. The aquifer sample had a nitrate of 12 milligrams per liter, whereas the borehole sample had a nitrate of 1.5 milligrams per liter. This EAM assessment quickly told us the biological process that was occurring in the well and why the nitrate results were variable over its history. The well, in the end, the well is full of biofilm and in need of cleaning, but the cleaning will not resolve the compliance issue for nitrate. EAMs, the takeaway message here is EAMs can be used as a quick assessment tool for assessing nitrification and denitrification in any system. So here I have a well example. It can be used in wastewater, it can be used in plumbing system to get an understanding of what kind of issue and what kind of biofilm is present in that system. Here's another well. This well has an excessive corrosion history and a need for costly repairs. This community would spend about $100,000 every 5 years to replace failed and corroded equipment. We wanted to do an investigation to figure out why. What we see in the EAMs here is stress conditions within the aquifer, and then less stress conditions within the borehole. Data show that nitrification is occurring in the well, which is process of actually converting ammonia into nitrate. And this is also basically known as ammonia oxidation. And it's happening because we have excess organic nitrogen in the water from the aquifer. Nitrate in the water, organic nitrogen in the water. So nitrate in water from the aquifer was a non-detect. Nitrate in the borehole sample was 2.5 milligrams per liter. So data suggests that the aquifer is starved of oxygen, which made it available, which then is made available in the well borehole and causes a reduction in stress and the generation of nitrate. So the nitrate generated in the well historically is basically the underlying cause of excessive corrosion. You have to keep in mind that all metal nitrates are highly soluble. So if I add nitrate to a system, that nitrate generated will cause dissolution then of metal components. That nitrate acts like nitric acid. This well was rehabilitated in 2016. We've done enhanced maintenance on it to control biofilm in the borehole over the last 4 years, and it has extended the life of the equipment. The ongoing maintenance suggests that the life of the equipment will be tripled with this enhanced maintenance, taking our $100,000 rehab investment and extending it. So instead of it every 5 years, now it's going to be about every 15 years. The takeaway message here is that enhanced maintenance for this well means less corrosion, means less need for adding chlorine at the discharge to control biofilm in the system, means less discolored water to the water distribution system, less colored water complaints for customers, and less formation of carcinogenic disinfection byproducts in the system. Often we don't need to do preliminary testing, just observation to determine the source of a problem or what samples should be tested. This example shows water collected from a municipal well shortly after pumping. Each bucket represents water collected over a 1 minute period of pumping, with buckets collected in a timed order from left to right, starting in the upper left-hand corner. Analysis shows heavy biofilm in the first 2 buckets, and microbe-induced corrosion in the cased region of the well, which correlates with the 1 minute and 2 minute buckets. If left unchecked, biofilm in this well will cause a casing failure, which could cost the community over $150,000 to repair. Water from this well is promoting, and also to note, the water from this well is promoting biofilm and corrosion of copper plumbing in the distribution system. By controlling this in the well, we can solve two problems, not only the corrosion in the well, but also the corrosion problem in the distribution system. And yes, water from the first 2 minutes of pumping was sent to the water distribution system for consumption. It's something that we see in many water systems. You just don't necessarily see it at the tap, unless you're really looking for it. In this example, we performed a corrosion investigation of a hotel plumbing system to assess the cause of copper corrosion. Samples from a particular room looked suspect based on EAM patterns there. Further analysis, we found that both those samples tested positive for Legionella, which can cause severe respiratory issues if inhaled. Routine flushing of the rooms and of the water service solved the Legionella and corrosion issue. This approach is somewhat contrary to published guidelines for Legionella control, which focus on testing for Legionella presence and reactionary chemical treatment of a system. But this approach of assessing biofilm presence using EAMs honed in on the underlying issue and allowed quick resolution. This approach also affords a means of assessing effectiveness of control methods and really should be used as the basis for developing water management plans for Legionella control. In this example, we see a major sewage collection system interceptor was experiencing accelerated corrosion. Interceptors are very large buried mains, typically 18 inches in diameter, 24 inches in diameter, that collect sewage from various parts of a city and convey it directly into the wastewater treatment plant. The most common culprit for such corrosion in sewers is sulfide oxidation that happens on the pipe surface, which creates sulfuric acid and dissolves concrete pipe. The preliminary data for this system, though, did not support this as the cause, so we investigated further to see the type of biofilm that grew on the pipe and ultimately was causing the corrosion. EAMs in this picture show secretions obtained from biofilm grown on concrete coupons that were hanging in the air in various parts of the system. These coupons were never in contact with sewage. They were placed in the system to replicate that part of the system seeing corrosion. So what we're seeing here is secretions from biofilm that formed on the surface of these concrete pipe. The data show a different type of biofilm grew in each part of the system, with the type that grew correlated with the sewage composition at that location. In the end, the corrosion was found to be primarily caused by ammonia oxidizing type biofilm, with the worst corrosion found near landfill leachate that was being added to the sewer system for treatment. The ammonia was off-gassing from the sewer, landing on the concrete pipe, ammonia oxidizing, create the nitrate, which then caused the corrosion. The takeaway point here is the investigation saved the sewage district about $500,000 per year on chemical treatment that would have never worked. The chemical treatment was for sulfide attack, not for ammonia attack. So we'll start wrapping it up here. The key to robust EAM data and interpretation comes down to these 7 points. The list emphasizes that robust protocols are needed in sample processing, handling, and cleaning of your equipment. The approach needs to be multidisciplinary, which means it needs to consider many sciences and fields of study, and even operations and how systems work. Interpretations always need context, namely an understanding of design and operational parameters of the system that's being analyzed. Interpretations need to consider and understand conflicting codes that may be at play, so we can really get down to what is the root cause and how do we solve it. And above all, critical thinking and question asking are needed to resolve problems, of which there are many, many, many in drinking water. We'll wrap back, we'll circle back to our concept. Hopefully you see that most water quality issues start at the source and are amplified by design, operation, and maintenance decisions or conflicting code requirements. Most water quality issues have a microbial biofilm component, which is typically overlooked by the codes or other entities when diagnosing a water quality issue. biofilm can be used, while biofilm is bad, it can be used as a diagnostic aid, which will allow you to separate a symptom from a problem so we can develop an appropriate solution. Nutrient conditions allow microbial growth and biofilm growth in a system, which starts right back at the source. And the balance then of the carbon, nitrogen, phosphorus in the water and the forms of nutrients presence will dictate the nature of the issue, which starts at the source and then can further change in the system. Excessive biofilm can cause non-compliance with drinking water regulations such as lead and copper, radium, disinfection byproducts, and volatile organic carbons. Our third concept then is optimized biofilm control will minimize water quality issues, which then can be accomplished through better treatment and better maintenance. This approach will minimize the potential for biofilm to grow at the source and minimize biofilm growth in the system. And through the result of this approach will mean less chemical usage, less taste and odor issues, and healthier water. So in summary, excitation-emission matrices provide a simple method for assessing the presence of biofilm and biostability in a system, which helps determine the underlying cause of a water quality issue, whether that issue is lead and copper plumbing corrosion, disinfection byproduct formation, radium in your water, metals released from aqua mineralogy, total coliform and E. coli positive results, or even a Legionella outbreak. Beams are an integral part of a system that helps us at WPI provide cost-effective solutions for our clients, because we're always separating the symptoms from the problems and looking at it as a holistic perspective using multiple disciplines. The important question that we should always be asking when assessing a water quality or corrosion issue is biofilm present? And if so, is it the source of the issue or the symptom of a much larger problem? By asking this question and doing the necessary assessment to determine if biofilm could be involved, targeted testing can be performed to better assess the underlying problem so that a cost-effective solution can be developed to resolve the underlying issue. With that, I'll turn it back over to Sherry, and I believe we're going to have questions.
Great. Thank you so much, Andy. I really enjoyed your presentation. Very dear to my heart, having done a lot with excitation-emission matrices myself. Really hope that folks got as much out of it as I did. We have a straightforward question up front here. How do you have your home supply flushed? Is it as simple as running the faucets?
Yep, that's a great question. We have developed a protocol. If you want to flush your own home, the simple thing to do is, if it's a 1-inch service, we'll want to try and get about 15 gallons per minute. So the simplest thing to do is to open up 2 outside hose spigots, put a hose on them and put them into a bucket. And you can time how fast it takes to fill the bucket. So you can try and you can estimate your flow rate then. And we often put those hoses then into a white bucket so we can see what kind of material is generated, and we flush it until it's clear. So that's a great question.
Oh, okay. Yeah, it's I know just from experience, like our lines, if we haven't used one of the bathrooms in a while, the faucet water, is discolored. So yep. You just kind of flush it until it's not.
And when we recommend that, then we recommend you flush that to the outside, and then we recommend that you flush your hot water system and then your cold water system. So you flush the whole house after you flush the service line.
So how would you know how often to do that? I guess it's unique for different areas, right?
Yeah. Well, one way you could do that is to clean your toilet tank when you do that, and then look in your toilet tank on a 3-month or 6-month basis. And if you see something growing there, what's growing in there is likely in the water system, and you can do that enhanced maintenance. The other thing would be is that you could flush it at 3-month period, and you would do the exact same thing into the white buckets. And if you have material developed there, 3 months is pretty good. But if you do it at 3 months and you don't see anything develop, well, then try it 6 months. And at 6 months you see something, well, then you want to do it between 3 and 6 months.
Okay, it's almost like ignorance is bliss, right? I mean, I don't know. Probably, if we took a poll of how many people have done anything with their water. You just assume, right, what's coming out of the tap is good, right? Especially if you have a water system, like most people will have softeners or purifiers, yep. Right?
Well, then what I often tell people is, you know, we clean our homes on a weekly basis. We change the oil in our car. We do preventative maintenance on that. Water systems shouldn't be any different. And, you know, if you are living in a part of the country where your water quality is challenging, you need to do more maintenance. If you're blessed to be living in a part of the country where you got pristine water, you have to do less maintenance. You know, somebody who builds a house in a desert is always doing dust control. Somebody who builds a house in the rainforest is always doing mold control. We just have to deal with the water that we're given and adjust our maintenance so that we have the most, you know, the most optimal water quality that we consume.
We have another question. You know, it's so funny because it's all going along with, like, you know, is it okay to, is it okay to drink softened and/or hot water out of my tap?
I always recommend to not drink hot water, mainly because hot water is not regulated. So none of the drinking water regulations that are established by the EPA or a state agency apply to hot water. And often when we analyze hot water, it will have elevated metals. So I always highly recommend never, ever drinking hot water from the tap. Softened water is okay as long as you're doing enhanced softener maintenance. And you understand that your softener is clean. If you don't understand, if you're not doing any softener maintenance, meaning every 3 months, 6 months, on a regular basis, cleaning that softener, then that softener can have high metals in it. So we only, and I clean my softener at home every 6 to 9 months. And if can you still see my screen?
Yes, there you go.
So I'm going to go back. This picture number 2 is after I backwashed and chemically cleaned my water softener, and that's after every 6 to 9 months. So that's full of metals. And in our area, we have arsenic in our water. So what we have in that brown water could be arsenic, but we definitely know we see copper and other metals in that water. So again, you can drink softened water as long as you know your softener is maintained optimally.
Okay, and probably many people are shaking their heads saying it is not. But, yeah. So another question, have you done EEMF, which I assume is fluorescence, to follow reclaimed water quality?
We have not. So yeah, you're talking about probably wastewater discharge, or so basically reclaimed water being the effluent from a wastewater plant, putting that back in for water consumption. We have not done that. But we have looked at raw water from rivers, which is somewhat reclaimed water, because that is the effluent from a previous wastewater plant that now is coming into a drinking water system. So we have tested surface waters, raw surface waters, and some of them are really, really challenging, and some of them are pretty good looking. So Lake Michigan by us is pretty decent looking. Lake Winnebago, pretty challenging. Mississippi River, pretty challenging. I think in one sample we pulled from a surface water, drinking water plant along Mississippi River, had over 1 million microbes per milliliter in that raw water. And the EAMs were probably in the 2 to 3 million raw fluorescence intensity units.
Oh, wow.
So it's, you know, and we see in Lake Michigan, if the lake is basically rough and being turned over by weather, we can actually see the upwelling of kind of biological activity in the sediments. And our EAMs, typically the raw water EAMs from Lake Michigan is in the 200 to 300,000 fluorescence intensity units, but we've seen it spike over 1 million, and it's really in the MVP EAM area when we have these upwelling events, you know, in Lake Michigan. But Lake Winnebago, Mississippi River, they're always just pegged all the way across. There's just so much decaying organic matter in that water, and just a really challenging to treat.
Yeah. Oh, the person clarified. Purple pipe water, reclaimed water. So I guess you addressed that.
Yeah, I think purple must mean that it's treated effluent that's used then for probably irrigation water in non-potable uses within a community system. We don't have any of that in Wisconsin, so I'm not familiar with it. But we have obviously looked at many different water supplies, and it really, we do see a considerable amount of treatment that's happening through the wastewater plant, but we'd have to look at that system specifically to accurately answer that question.
Well, and they know how to get in touch with you if they need some assistance.
Yeah.
So I definitely probably have a little different slant, because I didn't know if you could go to one of your, maybe the sewage one, where you show all the EAMs.
Yep, I'll get to it. That one?
Yeah, great. So, it's a lot. I know it's a lot to look at, and to me, based on what you've said, like if you look at the one where it's just a red blob, right?
Yep.
So that area, when you look at, you see these differences here. Obviously you've created that chart above, and I'm sure a lot of that, that's all proprietary, but so these fluorescence total product EAM and your decay product EAM, DP EAM, and MBP, right? Microbial byproduct. I think I figured this all out finally. Microbial byproduct EAM. All those numbers, then you've kind of found a way to basically take advantage of the wealth of information from each of these EAMs and pull information from the different areas, right? So the MBP EAM, you're doing something on the part of the EAM you showed us that represented those products, right? And then the DP, which is at longer wavelengths, right?
Yep.
You're doing something else to quantitate that. So that's really cool though, because visually you see things, but to be able to get a quantitation like that is valuable. That had to take a long time to develop that and with confidence.
Well, 4,000 samples or more. But yeah, and
I just wanted you to be able to stress to people, just the amount of work and samples and statistics and everything that went into this, right?
Exactly. And that's what we've been. And part of it is that we have to simplify this in our presentations to the clients. If we show them all the data, we would really confuse it. So we're only showing the MVP EAM, the DP EAM, and the TP EAM. But we've parsed this off into many different portions on the EAMs themselves. So we're just showing a summary, but like in this example, the part of the system that actually had the most corrosion was the S16 and S24 areas. And we can see in those the highest amount of EAM present. And these are secretions that were put into water, and we can see the highest microbial occurrence on the surface of the coupons. So the EAMs are the worst, the highest microbial occurrence, and it correlates the part of the system that had the most corrosion. And then with our biofilm activity test, our BAT test, we honed in and we could see them that they were metabolizing and burning ammonia products. So we could see that thing right there, that the high microbial occurrence on the surface of the coupon had lots of secretions. Those coupons were pretty rough shape. They were corroded, and oh, by the way, they were metabolizing the ammonia. And oh, right by the way, right in that area were two spots where landfills were dumping leachate into the collection system for treatment at the wastewater plant. So we used operations, engineering, microbiology, EAMs, and science to solve their problem. And it takes a lot to pull that together.
Which has got to be a lot of fun, right? And you probably have a pretty diverse team that works with you on that. Just because all the other numbers on that table, you're looking at pH, you're looking at conductivity, right? You're looking, so, there's a whole bunch of other testing you're doing and pulling in here to really make sense out of the trends you're seeing in these matrices.
Exactly. exactly. And you know, the EAMs are not an absolute measure. I don't want to give anybody that false hope, but they sure are a strong indication of where we need to look. And they're a strong indication of, boy, they're part of the problem, and they can raise a red flag. So yeah, it's lots and lots of data. I got a great team here. Each of us has a component that we do within this, and we've got redundancy. So if one person is sick, we have that coverage. But we're all conversant on, you know, how we generate these EAMs, how do we maintain the robust system, how do we interpret them, and every day it's a new discovery. We find a little nuance in the data that we've seen once before, and then it pops it rears its ugly head. It's like, we've seen that before. It must be something that we need to ask a question about, and you know, that's how we've come up with some of these discoveries and see these correlations. So I'm excited to see what the next 5 years is going to bring.
Yeah, that's exciting. So it looks like there's one more question. Why do you think the codes or, you know, legislations don't consider the microbial concept? Is there a pushback on that? Just, I think it sounds like they're wondering.
Yeah, no, it's a great question. It's one that I've often asked myself, and I think it comes down to the fact that what we're it's on this slide. You know, this is biofilm is complex. It's very, very complex, and this graphic representation is a simplified representation of a complex environment. And because we have all these different biological things that could be occurring, regulations can't say, oh, it's ammonia oxidation, oh, it's heterotrophs, oh, it's fermentation. So they can't pull it in. They can't wrap their head around it. And I think so how do you regulate something that's really hard to define what it is? And I think the other part of it is that there hasn't been a crazy enough scientist that came along to look at this until now. So I'm considering myself, you know, the mad scientist, in that I saw something strange many years ago in the pumping of a well, and it was discolored water at startup, but then it went away, and I basically asked the question of, why is that? And it took me down a rabbit hole of chasing, you know, why do we have these strange water quality issues? And what we found is that a lot of these strange water quality issues have a biofilm component. Biofilms are involved. Now our part is to educate the EPA and the regulatory agencies on what we're finding, so that they start considering the role of biofilm. Matter of fact, our group here, we have a teleconference with the EPA Region 5 next week on some of the stuff that we're doing, which hopefully will take us one step further in trying to get the regulatory agencies to understand biofilm. And maybe my hope is at some point in time that we'll recognize the role of biofilms as a cause of water quality problems, and we'll start addressing them in the codes, meaning that we have to look for them, we have to try and manage them versus throw chemical at them. So it's a great question. Thank you.
It seems like you're off to a great start on this, and you have the tests and you have some success to back it up. So we wish you the best with that. There's one more question, so I'll take it. It says, if the EAM of water is blank or low, does that mean my water is safe?
Well, that's a loaded question. Safe is a relative term, meaning that does it meet regulations or not? Because in my opinion, there is water that's considered, there's water that meets the regulations that is not considered safe. So that's one kind of aside. But if a water has a low EAM, it tells us basically that water is not stressed. So in this graphic here, I could have lots of planktonic growth because I have lots of nutrients in the water. Those nutrients are balanced, everybody is happy, therefore my EAMs are low. So we can have, you know, a really high microbial occurrence in a water that's going to have a low EAM because everybody's happy. So and that's one thing that we learned early on, is that the ATP test tells us, you know, how many bacteria are there in the water, The EAMS will tell us whether or not there's biofilm in the water or biological matter, and its basically physiological state. Is it stressed or is it happy? When I look at a low EAM and a low ATP, that's a good thing, because that tells me low bacteria in the water, low EAM, that if there is any bacteria in the water, that they're not stressed. So those two hand in hand are good. But a low E by itself without the bacterial count, that could give us a misleading result.
Great. Oh, good question. Thanks. Thanks, Katie. Well, Andy, I just want to thank you so much for sharing your work. I hope this gets folks excited about what you're doing and draws some attention to this new approach. And wanted to thank everyone else for your time and for joining us today. I think if Carlos switches back, I just have one closing slide. Let's see if that will pop up.
There it is. Nope.
Screen. There we go. Can we? Okay. Does everybody see the JASCO educational resources?
Yep.
Oh, perfect. Thanks. Okay. Yeah, we're not going to keep you. Just wanted to close and say, all of the webinars that we've been doing this year are available online. This will be available. Recordings will be available online, so you can access them again later. We have ebooks on Raman, fluorescence, FTIR, CD. If you wanted more background on fluorescence, there's a fluorescence webinar that was given earlier that you can pull up. In addition to these ebooks and tips and tricks, we have on our Learning Center webpage a great knowledge base to look up interesting applications that are relevant and instrumentation that's used for them. And I hope you take time to explore these resources, and please stay tuned for our next webinar, which is in the works. So we'll keep you posted and have that up on our Learning Center webpage when available. So thanks so much again, Andy, for your excellent talk today. And thank you all for joining us this afternoon. Have a great day.